Examples of circular motion. In this video, we will see how centripetal force and centripetal acceleration can be applied in practice, solving problems involving cases of vertical and horizontal circular motion. Before working on this video, you need to know the uniform circular motion. If necessary, you should refer to the following video, which covers this topic. Thanks for watching this video, and don't forget to like, subscribe to the channel, and activate the notifications. It's very important to the continuity of this channel. Pay attention in the following exercises. Constructing a free body diagram for the hanging mass, we see that the only forces on it are the tension T and gravity. From the forces on the hanging mass, we can immediately write that the tension in the string equals the weight. The tension is 9.89 newtons. This tension is also the central force exerted on the puck. The puck also has the force of gravity, its weight, pulling down on it, and the normal force pushing up on it. There is no net force in the vertical direction. These two forces just cancel out. All bodies moving in a circle must be acted upon by a force towards the center of the circle. However, this can be provided by many different forces. In this problem, the only radial force acting on the puck is tension, so the tension provides the net force on the puck required to keep it in uniform circular motion. We call this force the centripetal force. To find the speed of the puck, set the centripetal force equal to the tension and solve for the speed. Pay attention in the next example. Consider a car moving on a circular level road of radius 35 meters and with constant speed v. The coefficient of static friction between the tires and the dry pavement is 0.6. Let's draw a free body diagram. We see that the only forces on it are the frictional force, the gravity, and the normal force. There is no net force in the vertical direction. The normal force and the weight simply cancel each other. The net force in the horizontal direction is the friction force pointing toward the center of the circle. The friction acting between the tires and the road becomes the centripetal force to keep the car moving in a circular path. The frictional force is equal to the centripetal force. We start by substituting formulas for each side of the relationship. The friction force is related to the coefficient of friction and the normal reaction at the surface where friction occurs, and the normal force is equal to the weight. We can cancel both the m on either side. This rearranges to give a maximum speed. The fastest that the car can round the curve is 14.4 meters per second, or approximately 52 kilometers per hour. If it attempts to go faster, the force of static friction will be insufficient to prevent skidding. Pay attention in the next example. First of all, we draw a free body diagram. In cases in which forces are not parallel, it is convenient to consider components along perpendicular axes. Note that I choose the positive y-axis to point vertically upward and the positive x direction to point toward the center of the circular path. If we neglect the friction, the only forces on the car are the gravity and the normal force. The car's weight acts vertically downwards. The vertical component of the normal force must balance the downward weight of the car. And we can solve this equation for the normal force N. So it follows that the radial component of the normal force must supply the needed centripetal force in order for the car to move in a circular path. Substituting the expression for the normal force and cancelling the m, we can get the speed required. Pay attention in the next exercise. Let's start drawing a free body diagram. The only forces acting on the roller coaster car are the upward normal force exerted by the track on the roller coaster car and the downward force of gravity, the car's weight. The difference of these two is the centripetal force, and the centripetal force points towards the center. We can solve this equation for the normal force. The maximum speed at B corresponds to the case where the roller coaster just barely loses contact with the track. That means the normal force between the track and the roller coaster car is zero. With the normal force equal to zero, we can just cancel it, so we are left with only the weight and the centripetal force. We now solve for speed.